Rohini College of Engineering and Technology from Department of Civil Engineering. So this subject is in our civil engineering final year for 7th semester. So our subject title is C8703 Structural Design and Drawing. So I am Michael Devadurai, Assistant Professor. So now today we will see about the topic is design a flat slab with drop. So design of flat slab with drop. Then example, design of flat slab with drop for warehouse with a panel size of 6 meter into 6 meter. So in this question they will be directly given in panel size. Sometimes they will be given in warehouse size because that 20 meter and 20 meter or 25 meter and 25 meter. But in this question they will be given directly given as a panel size of 6 meter into 6 meter. So you can easily take as the size of the panel, and it's supported by a column 0.6 meter into 6 meter. So a column is a two sizes are given, so it will be taken as a rectangular or square column. So the same size we will take as a square column, and height 4 meter. So floor to floor height is the 4 meter, so it will be taken as a column height also. The site it's mild environment, then live load is 3 kN per meter square plus waterproof and floor finish load is given. Floor finish is for 2 kN per meter square is subjected. Then use M25 grade concrete and Fe 415 steel. So write the given data. So panel size is equal to directly given, so write it the 6 meter into 6 meter. Then column height size is equal to 600 mm into 600 mm. Then column height of column is 4 meter. Then live load is equal to 3 kN per meter square. They will be given in our question. So floor finish also given. So solution. So step number 1, determining the depth of slab. So it will formula is taken from our code book IS 456 2000 class number 31.2 and 24.2. So L by D, span by depth ratio, is equal to 0.8 into 40. So 40 means based on support of our slab position. So sometimes simply supported, it will take as one value. It will be in our flat slab is the continuous slab condition, so that will be taken as the 40. So 0.8 is the constant in our code book. So 40 is, it will be changed based on our subject. So 0.8 into 40 is equal to 32. Then minimum effective depth is equal to span by ratio. Ratio is the L by D ratio is 32. So apply that. So span value is also, you know that. So span panel size is the 6 meter. So 6000 mm. So 6000 divided by 32 is equal to minimum effective depth is 187.5 mm. Then as per IS 456 2000, minimum depth is equal to 125 mm. So hence safe. So use reinforcement bar 12 mm diabars, hence adopts 20 mm cover. So required depth is 187.5 plus then required depth is equal to 213.5 mm. So 12 is the diameter, so 12 divided by 2, this is our formula. Then let provides 220 mm depth. So D is equal to 220 minus cover slab is a 20 mm minus diameter by 2 is the formula. So D is equal to 194 mm. So step number 2, determining the dimensions of drop panel. So as per IS 456 2000 class number 31.2, the minimum length of the drop should be span by 3 value. So span by 3 means L by 3. So we know that the span value is a 6000 mm. So 6000 divided by 3 is equal to 2000 mm or 2 meter. Then minimum depth of drop panel is 1 by 4 into depth of slab. So depth of slab is equal to 220 mm. So 1 by 4 into 220 is equal to 55 mm. This is our minimum depth of drop panel. Then provide drop panel is equal to 60 mm. So that will be 55 mm, but we can assume that's the 60 mm. Then total depth of the drop panel is equal to the depth of slab plus drop panel depth 60 mm. So 220 plus 60 is equal to 280 mm. It will be greater than 12.5 into 220. So width of the columns is equal to L by 2. So span length is, we know that 6000 mm divided by 2 is equal to 3000 mm. So step number 3, load calculation. So first one, the self weight of slab in the middle strip. So self-weighted slab is equal to 0.22 into 25. 25 is the unit weight of concrete. So 0.22 is the depth of the slab. Okay, then dead load due to drop panel. So drop panel means the size of the drop panel is 60 mm. So it will be converted into 0.06 meter. So live load is equal to 3 kN per meter square. It will be given in our question. Then floor fin is equal to 1 kN per meter square. So total load is equal to W is equal to add the all the remaining loads. So 11 kN per meter square. Then factor load W is equal to 1.5 is the factor load. So 1.5 into total load is equal to 16.5 kN per meter square. Then finding out the clear span value. So Ln is equal to 6 is our panel size. So 0.6 is our column size. So minus that. So 6 minus 0.6 is equal to 5.4 meter. The design load is WU into L into Ln. This formula is in our code book, page number 55. So mark it. Then W is the 16.5 and L is the span length 6 meter and Ln is the 5.4 meter. So design load is 534.6 kilonewton. Then step number 4, calculation for bending moment. So design static moment MO is equal to WLN by 8. So this formula is in our code book, page number 55. So 534.6 into 5.4 divided by 8. This is our apply the values. So got the bending moment. So total negative moment is the 65% and the positive moment is the remaining 35%. So it will be taken from our total moment. So 65% for static moment and 35% for static moment in a positive design moment. So it will be negative design moment is 234.55 kN/meter and positive design moment is 126.3 kN/meter. Then negative moment at column strip. So it will be separate into for column strip and middle strip. Because negative moment for column strip is 75% and positive moment for column strip is 60%. Okay. So 75% means 0.75 divided by 100 into 234.55. So negative moment for column strip is 175.912 kN/meter. Then positive moment at column strip is equal to 60%. So 60% means 60 by 100 is equal to 0.6 into 126.3. That is total negative design moment. So positive moment for column strip is 75.78 kN/meter. The negative moment at middle strip is equal to 234 minus 55 minus 175. So negative moment means from positive moment minus negative moment. So you got the 58.638 kN/meter. So positive moment is already we find out the column strip. That positive moment is 126. So 126 minus normal moment 75.78. So you got the 50.52 kN/meter. Then step number 5, checking of the slab depth due to bending. So we need to check the depth of the slab in this step. So we know that the simple formula D is equal to root of mu by 0.138 FCK into B or the whole power 0.5. Anything you will be take. So mu is the take will be maximum moment. So our maximum moment is 175.912. Then 0.13 is the constant. Then FCK is the 25. It will be given in our question. Then B is equal to 3000 mm. So small d is equal to 130.4 mm. So our effective depth provided is 194 mm. So we can provide a 194 mm, but it will be 130. It will be safe for the slab. So hence the provided depth is sufficient. And step number 6, checking for punching shear. So punching shear is first finding out the effective depth of drop. So effective depth at drop portion. So 194 plus 60. 60 is the thickness of drop panel. So 194 plus the effective depth. So add the two values. It will be given the effective depth at drop is equal to 254 mm. Then critical section is a distance. So critical section is d by 2. This is one formula. So d by 2 is equal to d is the 254 mm divided by 2 to 127 mm. So from column face, perimeter of critical section BO, we have mentioned as a BO is equal to the formula. Perimeter formula is 4 into A plus D. A is the column size and D is the effective depth of drop panel. So A is equal to 600 mm then D is equal to 254 mm. You got the perimeter of critical section is 3416 mm. Then shear force for this plane V is equal to load by area, the simple format, but load into distance, load W. So L into L is the panel size, and A plus D into A plus D. This is the formula for finding out the shear force for this plane. So L is the panel size, if you know that 6 meter into 6 meter. Then A is the size of the column. Then D is the effective depth. So apply the value of shear force is 581.96 kilonewton. Then nominal shear stress is equal to load by area, simple formula. So load is equal to be taken as the shear force, and area is the B into D. So B is the BO, perimeter section, and D is the effective section. So effective depth of drop. So we know all the values. So apply the values in our formula. We got the nominal shear stress. So nominal shear stress is 0.67 Newton per mm square. So it will be less than 1.25 mm. So hence the slab is safe from punching shear reinforcement. So punching shear is no need that. Then step number 7, design of reinforcement column strip. Then finding of the AST values. So our maximum negative reinforcement is equal to 175.9 mm. Then effective depth of drop panel is equal to 255 mm. So apply this formula is different, mu by BD square. Okay, so mu is equal to moment, maximum negative reinforcement moment, and B is the width of the column strip, and D is the effective depth of drop panel. So 175 into 10 power 6, B is equal to 3000 mm, and D is equal to 255 mm. Apply the value, you got a 0.908. So this is taken from our SP16 code book from table 3. See that percentage of reinforcement is 0.26. Then AST is equal to that value 0 PT by 100 into B into D. Okay, so then given as a 2007.1 mm square. For 300 mm width spacing is apply the spacing value is only change is equal to 169 mm. Then provide 12 mm dia bar at 160 mm spacing. We take as a 170 mm or 160 anything. At the top of the faces slab over the columns in the column strip. So actually our column strip is provided in the over the column strip. Then reinforcement for positive moment in the column strip. So ASD is equal to mu by 0.8 Fy into D. So apply all the values. You got the ASD is equal to 1176.56 mm square. So minimum ASD is equal to 0.12 percentage of B into D. So spacing is equal to same formula, pi d square before into B divided by ASD. So is equal to 288.37 mm. So provide 12 mm dia bar at 288.37, it will be that. So you can assume as 290 or 280 anything, or 285 is also you can take. So provide 12 mm dia bar at 280 mm, center to center distance, spacing at bottom in the column strip. So see the diagram. This is our reinforcement details. So four corners are the column strip column. The center one is the middle strip column. Then mark the values. For column strip is the main reinforcement is the 12 mm dia bar at 160 mm center to center distance. For middle strip is the 10 mm dia bar at 250 mm center to center distance. And without the middle strip is 3000 mm. So drop width, see the drop width and middle strip and drop width also. Then reinforcement for negative bending moment. So M is equal to, for negative bending moment is 58.638 kilonewton meter. Then AST formula is a known same formula. So apply all the values if you know that. So let's provide 10 mm dia bars. So finding out the spacing using the same formula for spacing. So spacing, apply the values 258.8 mm square. So provide 10 mm dia bar at 250 mm center to center distance at top in the middle strip. Then reinforcement for positive moment. So take the positive moment value 50.52. So same AST formula, same spacing formula. So in this step we can provide 10 mm dia bars and 250 mm center to center distance in bottom of the middle strip. So the same reinforcement middle strip at the top and bottom. So see the reinforcement details, column strip and middle strip. So first one the column strip. So providing main reinforcement is 12 mm at 160 mm center distance, and middle strip is 10 mm dia bar at 250 mm center to center distance. Thank you.